welcome you, sir. You can
Yeah.
continue the session.
So shall I continue?
Yeah, yes, sir. Yes, sir.
All right. Thank you. So can I share? Right. All right. Can you guys see my slide? So is it visible?
Yes, sir.
All right. Thank you. All right. Okay. So all right. So good evening. So here in Malaysia, good evening. So I believe here it will be there. It will be good afternoon, right? All right. Okay.
No,
Thank
here
you.
also.
Yeah. Okay. So my name Azhar Muhammad Ibrahim. So I'm associate professor at the International Islamic University Malaysia under the Department of Mechatronics Engineering. Okay. So I'm also the coordinator of Advanced Multi-Agent System Lab under the Mechatronics Engineering Lab. Okay. So here I have been given the topic on the intelligent transport system and also the video analytics. So I'll be talking on the embedded AI. So because on the transportation system, it is very important for the robotics, and I feel it is very very important for me to give some very introduction of the reinforcement learning, and also give you some the basic the coding for this reinforcement learning. And as you guys might know, this deep reinforcement learning is such an advanced, and it is booming right now for in a way that so the robotics, intelligent robotics, it will be very when it's applied with the deep reinforcement learning, we can achieve the self-learning algorithm, and it can where the robots can learn by itself. That's the spirit. Okay, so I'll begin with the some very good introduction of the artificial general intelligence. So it is said that the researchers at DeepMind suggest
Dear sir,
reinforcement learning
can I request to make your presentation in a presenter view, slideshow?
in a slideshow.
Yeah,
So
full
right now it
screen.
is not in the slideshow.
No, it is showing in the slide by slide. If you can click slideshow, because the text appears very small.
All right. Okay. Yes. Now, okay. Still same.
Still same, sir.
Oh, I'm not sure. Right.
I think you have to
I
make
stop present and then
you
I
have to
share
make
it.
the slideshow first, then share the screen.
All right. Okay. I just said share the entire screen. That's much better. So now, okay?
Yes, sir.
All right, thank you. Okay, so the researchers at DeepMind suggest reinforcement learning will be the main algorithm in which that it can replicate reward maximization as seen in nature and can eventually lead to artificial general intelligence. And you guys also might know that right now, in the OT also they have been claiming that this already in a way to achieve the AGI. There's been some debate going on there. Okay, so here I would like to talk on the reinforcement learning. So if we know also the AlphaGo is a computer program, the in a that plays the board game Go, and then it was developed in by DeepMind, and it reinforcement learning together with the supervised learning and MCTS. So normally people will use the in the agents based or robotics the learning where the robots can learn from by itself by the maximizing the reward. They will use the reinforcement learning to make sure the robot can learn by itself. While in the like in the chat GPT, so in the agent based, normally if they have trained by using supervised, so they will try to embed with reinforcement learning so that the agents that the developed agents can learn by time. When it receive the feedback, it will learn. When it receive the feedback, it will learn, and then it will update its knowledge. So that's the aim lah. That's the somehow they've been using this reinforcement learning. Okay, so this all of let's watch this thing, so to get some picture of reinforcement learning. As we can see here, when the chicken bite the pink color piece of paper, then it receives some food. So it is trained like that. So then by time the chicken also will know it will bite the pink color paper, then only the it will receive the food. So that's how the training is happen in everywhere. So like here we human also normally, whatever that we have the goal, we will try to maximize our reward. So that's the fundamental of the reinforcement learning. Reinforcement learning is a machine learning training method to on rewarding desired behaviors and to maximize the gain. So that's the fundamental idea. So in the reinforcement learning, so we will have the agents, we'll have the environment. So when the agent observe the environment and then try to do some act, it put some action into that. Okay, so then the agent will step to another state. So on that state, the agent will receive the reward. So that's the rotating process of the basic reinforcement learning, where the agent do some action, it will be in the environment, it will be in the new state, then it will receive the reward, and then it goes up to the agent again, it will be this process will continue. So this is how the basic of reinforcement learning comes into the world of programming. Okay, so as we can see here, so for instance, the robot is looking for the battery to recharge. The robot needs to move. It needs to find the way to reach there. So this is the environment. This is the agent. It will be the robot. The agent can be anything. It is not only the robot. Okay, ChatGPT also is an agent. Okay, so everywhere now is a agentic. They say 2035 will be the agentic world, agentic time for the agentic AI. Okay, so let's see what will happen in the near future. Okay, so the robot see the environment, and then it will do some action. It will do some action, and then it will reach to the new location. For example, to make it simple, the robot will reach to the next location. That will be the new state. In that state, the robot will receive some reward or some punishment. So that's how the robot moves. Okay, and then it will do another action, another state, another reward. That's how it continues. So when we see the people, who have the puppies and everything, so they will train also by using the reward. That's why this is a very, very promising area. It will boom, inshallah. It will boom in the near future. Very soon it will boom. Okay, so we can see here the reward. So when the robot is getting near to the battery, it will receive positive reward. While if the robot is getting far away from the battery, then it will receive some punishment. Okay, so this is the basic of the reinforcement learning. Okay, so it will learn by trial and error through reward and punishment. The program learns by playing the millions of times. It will take time to train the robots. That's why, so in one of the talk, so it is our Prof. Yan Lechun also mentioned that even to train the robot, to train the agent to make the robot or car understand that going fast is very, very, is going fast, it is not good. It will take enormous training times. It is not that easy. It is not that easy. For us also, we learn how we know that going fast in the car, it is not safe. It is quite dangerous. How we know? By time, even from our childhood, we've been told by our parents, we've been told by our teachers, our friends. Sometimes the environment also make us be like to put our act in a negative way. So why people are doing? Because people are thinking that they're gaining some reward also. So means that it is a negative reward for them lah. Negative reward we perceive as a negative reward, but for them it looks like a positive rewards, positive things that they're gaining something. Right? That's the things that So that's why in the agentic also, when the over time it will learn to maximize the reward. It will reach the convergence where it already reached the maximum reward that it will attain. Okay, so that's the fundamental idea. So let's move. Let's see this video of the Xiaomi. I like to share these things because some of you may be already very good already. Understand? So some of you maybe it's a new thing. Okay, so let's take into here this one. This is a cyber one from Xiaomi. So it falls down, and then it learns again. Okay, so when we see at the first part of the video, the robot, it was shown that the robot learns to walk. And then now the robot identify the obstacle, and then the robot cannot walk like that, right? It need to do something. The robot identify this is it has some obstacle, then it need to maneuver, it need to avoid that obstacle. Let me forward it. It observes some ants are moving. So, okay. So to achieve, of course, we all know that it is not a single algorithm will make everything perfect. No. So all of the algorithms, it is very, very indeed, it will be a combination of algorithm if we want some powerful AI agents. So that's how we see here also. It has some image processing. It has some machine learning in the classification, recognition, and some some decision making. And also we can see also deep reinforcement learning also in the of course Xiaomi never claimed, right? But this is how when we see we can somehow we can summarize this. Maybe the algorithms are there. All right. So it will take this flower, and then in one of the stage, it brings that flower to that to its boss. All right. Okay. So it's very funny, but it's good, So I would like to share. I'm sharing because I want to see how to for the reinforcement learning can be applied also everywhere. Okay. So this is the final summary before I move. Okay, so the agents, it will observe, select action using policy. Of course, we have the policy. Okay, it is not that easy, right? To maximize the reward, and then put the action. It will get reward or point penalty, and then it will update its policy, and then it will continue until it reaches the optimal policy or the maximized reward. Okay, so for instance here, so this is the robot. It wants to move to this goal. If it moves to that goal, it will receive +1. Okay, so the robot move, learn, and finally it comes to know that okay, to move there, so it needs to follow by time, it needs to follow some certain things. It will know that okay, so this is how the robot needs to move. Okay, so let's say by time the robot learns already, it already reached in this point, and then it puts okay, so to +1. So whatever the path that leads to that goal, it will put +1. Okay, so but how if the robot, that's when the robot is here, but how if the robot is here? So after we put the mapping, we put all the reward, +1, +1. This is the path, but now the robot again confused. So in this location, shall I move to the right or to the down? Now it again confused. So now what to do? So that's the beginning point. So the dynamic programming, the Bellman equation from the 1953. This is the fundamental of the reinforcement learning, where the Sir Richard Ernest Bellman, he introduced this Bellman equation, where the reward plus with the discounting factor of the value for the next state. Okay, so I'm not going to put all the theoretical. I'm just wanted to show only what will happen by using this Bellman equation. Okay, so if we use this Bellman equation using this discount also, so what will happen is this: from 1 it discounted to 0.9, 0.81, 0.73, 0.66. So when the robot moves nearer to the goal, it will get more reward. So this is the fundamental idea of the Bellman equation. Okay, so let's move. So this is the plan. This is not the policy, this is the plan only. Okay, if the robot is here, it moves to here and then moves here. So this is the plan, how the robot should navigate in this location, in this area, okay, in this environment. This is the plan. Okay, so let's move further. So the plan is, what is the plan and what is the policy? So policy will be, the plan is a sequence of actions only. Okay, but policy is the thing that it will make the robot to decide, and then it will optimize by time. Okay, so this is the deterministic scenario where the robot when it wanted to move to the up, it will move to the up. It will move to the up. Okay, it wants to move to up, it will move to the up, it will reach the up. Okay, so but in the real world, let's see this Pac-Man. Let's see this Pac-Man. The ghosts are scattered. Okay, so when the Pac-Man wanted to move, sometimes the ghosts are there. When it wanted to move, it is not happening, that the moves is not happening. So I'm just giving this example only. In the real world scenario, when the agent wants to move or agent wants to take another action, sometimes it is not deterministic. So a lot of non-deterministic are there. The randomness are there. The noise are there. So all these things we need to consider also when we develop this agentic kind of deep reinforcement learning or reinforcement learning. Okay, so this is the actual scenario. So when the robot wants to move up, it is not certain that the robot will reach there. Can also the robot, maybe 80% it reach there. It can be also 10% to the fire, or 10% it will hit the obstacle or column or anything. Okay, so that's the randomness. Randomness is available at anywhere. It is not only at one point only. So that's where the Markov decision process comes in, where the probabilistic scenario, it comes into the picture. Okay, so I'm not going into the equation, do not worry. So this just, I wanted to introduce how the probabilistic comes to the point. So with the probabilistic, so this is the plan as I said earlier. Okay, so with the probabilistic, so this is how the AI will looks. So this is so this is the in the one of the coding scenario that has been implemented by if I'm not mistaken, Berkeley Edu. Okay, so where it found that at the beginning, the robot is not moving into the fire, but the robot is not moving at this location, at particularly in this location. The robot is not moving up. It should move up, but the robot moving to the left. So why is it? This is based on Markov decision process. Anyone maybe wanted to try or to guess something? Why is that happening? The AI is deciding like this. Yeah, because of this randomness, right? So you might be guessing that this might be because of the randomness that has been introduced there. Because of this randomness, okay, so if the robot wants it to move up, it has the chance that, of course, it has the chance, 80% of the chance to move up, it will reach there. But there is a 10%. When the robot wanted to move up, it might reach to the pit, the fire pit. So, right. So that's where the agent, by time, it will learn. Oh, if I jump to the up, I may reach to the up, which is very good. I'll be very near to the goal. But at the same time, I also might end up in the pit. So this is not good. By time, the robot will know, the agent will know. So I need to move to the left. If I move to the left, what will happen? The robot will hit the obstacle and then it will be at the same point. But there is a chance the robot will move to the up. There is a chance, but no chance to move to the fire pit. So that's how, this is how AI evolved. AI, when we say agents, AI agents evolve, at the beginning by using this MDP, Markov decision process. Okay, so that's how, this is how the AI agents evolve. Okay, so let's look. So this is by using this MDP. Okay, so this is how it looks like. Okay, so and the rewards also. Let's move to the rewards. Rewards are signals given to an agent to indicate the desirability of a particular state or action. So we need to also somehow design the reward so that the agent will know to maximize the reward. And there is also living penalty rewards. Why we do have these living penalty rewards? As you can see here, okay, so let's say the robot is here. Okay, maybe here, unless I move back. Okay, so let's say the robot is here, 0.9. Okay, so when the robot is trying to move up, sometimes it reaches there, but sometimes it can also reach in the fire pit. And then if I move left, most of the time I will hit the obstacle. Some of the time I will reach at the up. But if I go down, I'm receiving less reward. Why not? I just stay there. It is also very safe. That's why the training, when you train the agents, sometimes you will observe that the robot is just idling there. Just, getting there only. They're not moving because of this. So we need to look into the, the reward functions, our policy and everything, so that the robot will move. So the training, so if we observe, I think the recent video by NVIDIA, they are training the agents of moving or something. It takes a lot of time. So to train the robot or to train the agents to learn, it will take a lot of time. Not that easily can be done. All right. Okay, so let's move again. So this is where it comes, the living penalty rewards. So that we want to avoid the agents idling there. The agents will find how that. So rather than I move later, I'm there. I settle down here. I'll get some rewards. That's much better than taking the risk. So we shouldn't avoid, right? We need to avoid those kind of scenarios. That's why the researchers, they have come out with the living penalty rewards. And then there is a sports rewards. Sports rewards means that when it reach the milestone, when it getting very near to the robot or go to the goal, or it maybe in the half of the goal, or maybe it reach at the goal. So we give some lump sum, a lot of there's some good amount of reward we give. So that's we call sports reward. And then we can also have the dance rewards. Dance rewards means that so that the it will makes when the robot getting, for instance, when the robot getting near to the goal, okay, when the agents is achieving that goal. So when it is achieving, it is getting near in achieving the goal, so it might getting more rewards. So that's we call a dance rewards. Okay, so for instance, this is the rewards. Past rewards means when it reach the goal, it receive the 1,000, for instance lah. Okay, so dance reward means when it getting nearer to the goal, it will reach more rewards. So this is what we call dance rewards. Dance rewards. Okay, so let's move. So this is an example of living penalty. So this is an example, so that the when we introduce, the robot cannot stay there. If the robot stay there, it will receive the minus point. So by time, so every time the robot stay there, it will receive minus. The robot will try to avoid. The robot will try to avoid based on the policy. So based on the policy, the robot will try to avoid, because we have the policy that governing the movement of the robot. Okay, so the robot will try to avoid those kind of the punishments. So this is where the idea of living penalty was there. Okay, so let's see what will happen, for instance, when we have a living penalty of 0. So this is where living penalty of 0, where, so we see at the beginning, right, the robot moved to the left. So why? The robot wanted to avoid the fire pit. If it moves up, sometimes it can reach also in the fire pit. So that's why it take the decision to the left. So the idea is when it hits the obstacle, most of the time it will hit the obstacle, but some of the time it will reach to the up, but no chances to get to the fire pit. That's that's why this is the decision when the living penalty is not there. Okay, but let's see what will happen when the living penalty is negative 0.04. So now when we have the negative 0.04, so now we can fix this. We can fix this. Now the robot again move up. Why? Because if the robot is here, so it will receive the minus point, rather than going left. That better I'm going up. Better I'm going up because of this living penalty. Okay, so let's see what will happen when the reward is the living penalty is negative 0.5. So now we have introduced around 10-fold already. Minus 10.5 and negative 0.5, the living penalty. See, so what's happening here? It will try to avoid. It will try to maximize. It will try to move faster to the goal. That's what we can see here. So originally the robot is moving here. Because it doesn't have the the desire to move here, because here we have the randomness of the fire pit. So it moved like this to the goal. But here, when we increase the reward, the living penalty, to the negative 0.5, what is happening there? Even here, the robot change. So we have two paths here. And then another one is like this. Right. So this is when we introduce we increase the living penalty. Okay, to make our understanding better, so what will happen if the living penalty is negative 10? Anyone might guess? Okay, and anyone, I'm showing you that is the original one. The reward is getting here positive 1, here is minus 1. Okay, so what will happen when the living penalty becomes negative 10? Alright. So this is what will happen. So you see, at this location, the robot feels that better I move to the fire pit rather than I continue my path. Because move to the fire pit, it will receive only -1. But when I still in my own place, I'm getting more punishment. So they are not like human, we have this pain and everything. So mainly because of this training and also reward and punishment. That's why our modeling should be correct. Our modeling of the reward, our modeling of the policy. So that's all should be very, very important in make sure that our agents are properly working. So for instance, in the self-driving car, so you need to train a lot of time. You need to examine in a lot of conditions. So this is very, very basic. This is very, very basic. As you can see here, what is happening when the living or just only living reward. We are not yet putting the dense rewards, sparse rewards. Where there are a lot of things. The policy. This is only reinforcement learning. This is not yet deep reinforcement learning. Okay, so we can see a lot of things are happening. So that's why we need to examine a lot of things, so that our agents, we will know what it will take the decision, because the AI is taking decision by its own. So that's why some people are very, 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 they're studying also the pattern of ChatGPT answering the question, because the ChatGPT also is learning by time. The learning, the originally it's passed by using the transformer, but it takes also the learning by time. It is by the feedback. It is they have introduced the reinforcement learning also there. So learning by time. So it will, we need to examine how it is, how the agents are deciding, so that we will know. So we will have some kind of picture lah, how the agents are moving, agents are deciding, so that we can guide people also, because some of the applications are people oriented. Some of our applications are for the people. So we don't want any harm, any dangerous effects for the people. So we need to avoid, so that when we train, we need to do a lot of training. We need to observe a lot of things. Yeah, I understand money is kind of things, that for a lot of, when we want to train for a long time, so it will have some negative point of view, also negative effect also for us. But that's the idea, because when it is for the people, for the benefit of the people, so we want to minimize the the negative effect also. So this is the comparison of the reward. We have the living reward, sparse reward, dense reward. Okay, so let's move to the Q learning. So that's how reinforcement learning of evolution of reinforcement learning. So as I said, that I feel that when people understand the basic of this, the learning, the training and everything, so they will have some kind of a lot of things they can do. Okay, so Q learning is a value-based reinforcement learning algorithm used to find the optimal action selection policy for any given MDP problem. Okay, this is one of kind of reinforcement learning, value-based reinforcement learning. So used to find the optimized action selection policy. Okay, the goal is to maximize the Q value to find the optimal action. Okay, so this is the equation. As I said, I won't go into the equation. Okay, so in the policy, in the Q learning, we have exploration and exploitation. So in a lot of algorithms, there will be exploration and exploitation. Exploration, trying new actions. What we mean by exploration? The agents are trying new actions to discover their effects. Sometimes, so in rule-based, in heuristic, so agents are not being give freedom to try the new actions. So then won't know what it will receive when it try the new actions. Here, that's why exploration also is very important. Sometimes normally, so what the researchers will do at the beginning, they will maximize the exploration so that the agents can try to move, and by the time it will know, it will understand. Uh, okay, exploitation means known information to maximize the reward. So means that it will select the action based on the highest Q value that had been stored earlier. So at the beginning, we will have some kind of initialization, and then by exploration and exploitation, that's how the agents will make the perfect, to learn the perfect the path in the robotics. Like the same agents also same. Okay, so normally what researchers will do at the beginning, they will try to maximize the exploration actions, and by time it will try to decay. So one of the fundamental, we can say, the basic of the policy is a epsilon greedy policy. Epsilon greedy policy, where we have the probability of choosing the random actions, right? So means we have with one probability, let's say with the epsilon probability, the agent will explore. Then the rest will be the exploitation. So normally, what will the researchers will do? They will have the decay strategy, gradually reduce the epsilon over time. Why? To shift from exploration to exploitation. So at the beginning, we want more exploration. Towards the end, let's say the robot already know how to reach, how to get the goal, and then at that time also, you want the robot to explore. Then the robot won't learn, right? Won't learn to reach or get the goal. So that's why we need to have some kind of like adaptive. This is adaptive epsilon greedy. So means at the beginning more exploration, and then towards the end very minimum exploration. All right. Okay. So today's the coding will be the basic coding on how, for instance, whatever that I'm showing here, that's what we will see in the coding also. How the agents can move to the goal by using the reinforcement learning. Okay. So for instance, here the agents at here at 0, 0, at 0. Let's say this is a 0, 0. So even though my example is more towards the robotics, the movement of the robotics, but I believe in everywhere that all the applications will be same. So when you want to apply the deep reinforcement learning for the camera for itself, for to find the optimal location so that it will capture the best moment, for instance. So that's how that's also can. So normally people use the reinforcement learning where the decision making for the uncertainty is there. Decision making, or to optimize the decision also, it will be there. Okay. Okay. So let's understand. Some of you may be already very expert in this. Okay. But some of you, this will be the first time, for instance. Okay. So let's say this is the 0, 0. The robot is here. The robot wanted to move here. This is the goal. Okay. So we have here the state, and then the Q values is negative 0.5, 0.2, 0.3, negative 0.30. Okay. This is the means that if it is left, negative 0.5, maybe down, up, negative 0.2, going down, negative 0.3, going right, 0. So that will be the Q values for each location, for each state, up, down, left, and right. Okay, so policy decision, epsilon 0.1, so 90% chance of choosing right. So this is the 10% of random action, 90% of choosing right. Why right? Because as we can see here, the right has the highest Q value. So at that location, normally it will have a 4 in the basic of Q learning. Basic of Q learning, it will have 4 tables: one for the up only, one for the down only, one for the left only, one for the right only. So at that location, at this location, it turns out that moving to the right only, it has the highest value. Okay, so if the robot at that time it is following the epsilon, then it will take random action. Random computer will select the quantum in randomly. Okay, but if that at that time it is 90%. So means, of course, right, you understand, right, how these things will work in the computer, right? So means that it will have 10% of probability in the randomness to choose exploration, and then 90% for instance, right, in this example, 90% for the exploitation. Means this 90% for the exploitation, the 10% for the exploration. Okay, so 90% it will choose the right. So the robot computer will decide. So if it is epsilon, it will take the any random action. If it is exploitation, it will move to the right. Okay, so and then okay, so there's the example, and then this is the leaving penalty. So this is the example that okay, this for here. This is where the example here. This is the -1. So the leaving penalty, if the robot stays there, it will receive the leaving penalty punishment. And then if it reached the goal, it will get 10. So okay, so that's how, and then this is how the initialization and everything. Okay, so how the robot will move at one point to one point. Okay, so this is all the Q values. So why not let's move to the code in the Google Colab. I have passed the Google Colab code right at the beginning. So let's try to implement that code. Okay, so before we move to the code, I would like to show some of the, some of our works in this DRL, so that I may improve your understanding. So for instance here, this is unconverged. When the training is there, this is by using the MATLAB. We have our own DRL codes there, means the DRL with our heuristic functions. So this is where, when the robot is not, unconverged, it's trying to move. You see, the robot is that robot is already hit the obstacle. It just stopped. So this robot also now already hit the obstacle. It stopped again. So again, I show you. So this robot is maybe it looks very small, but we took all the dimensions same like Turtlebot, and then this is the LiDAR. All the things are moved. We never put anything the robot should move like this. No, this is purely by using DRL and our algorithm for heuristic ones.
If possible, can you zoom the screen?
Again?
If possible, can you zoom the screen?
Zoom the screen, huh? Okay. Okay. So you see the first robot is the second robot already hit the wall. The first robot trying to move here and there. It's not. That's how at the beginning the training will take some time. So even for us also, it will, even with our GPU and 64 gigabyte of the memory, a lot of crashes happening here and there. Okay, so after some time it will converge. So when it converge, you can see it's very fast. Even this one we have a moving obstacles. The 3, 4 is the moving obstacles, the dynamic obstacle, and 1 and 2 is the robot itself. So we can see here. The robot already know how to move to the exit, to its location. So this is the converged model. So the robot will know by time how to move, and then how to whatever the in the environment itself. For instance, here we do have the dynamic obstacles and the static obstacles also. The robot needs to move to reach to the goal point. Okay, so I'll show another. This is not only for this, is for human agents. for human agents, where we have all the agents. This is the 100 agents. They're coming to the exit point. So this work we published last year in the Advanced Engineering Informatics, our DRL with the fuzzy logic. So all these agents, as we can see here, we also observe some phenomena where some of the agents are not moving at the beginning. So are not moving at the beginning. They are more observing at the far, at the middle, at the mid. You know, that's because of the AI agents. Otherwise, of course, they will try to move at the beginning already. So they try to observe what's happening there. How to maximize their reward. Okay, so this is the latest one. We have implemented one of our in the robot by using the DRL. So it will deviate, it will avoid the obstacle, and also it will reach the goal point. So by using DRL, you can see, it won't the path is not fixed. The path is not fixed. It is up to the robot at that time. But of course, it want to reach the goal point. All right. So as I said, I have showed about the Q learning, but I didn't say about the DRL. So when we have the Q states, right? When we have the Q states, all the Q states, right? All the Q states now we put in the network. We'll have two network in the deep QN. So the fundamental of the DRL, the reinforcement learning, we have the Q value, and then when we transform to the deep learning, we introduce the deep learning in the reinforcement learning. So we have deep QN, deep Q network, where all the Q space, all the Q values now been in the network itself. The network will update all the Q values. So we'll have the two networks. One is the target network, and then another one, the network for the original decision. And then sometimes it will have the target network, so that we can calculate the loss function and everything. So that's how the DRL, and then they have introduced the DDPG, deep deterministic policy gradient, and then we have the soft actor critic, and then we have asynchronous soft actor critic, A3C, A2C. So a lot of things, they are moving ahead in the DRL actions. So this is where I have okay, before we move into the code, so I would like to ask if you have any questions that you want to ask. So feel free to ask. I'll try my best to answer. So anyone, you want to ask any questions? You can put in the chat box so I can read. I'll try to answer. All right. Okay. So if not question, let's move to the code. Let's see. This is the basic code I have prepared. This I prepared for my class, actually, my class of the reinforcement learning. So, but it's very, very good. So it took time for me to set this code. So let's move here. So can you see my code? If I have passed this code also, this exact code. If you can run the code. Anyone? Are you trying? Any feedback? Okay, if you run the code, it will take some, because this is very basic. This is the grid that I showed earlier. This is the exact one. I am implementing this code for this grid world. Where the robot is here, the agent needs to move to the desired position, the green colored position. Also, okay, so let's see how the DRL is working, right? So that we have sometimes the basic code, it will give some very, very good understanding. So let's see, because this is very basic, it won't take much time for the robot or for the agent to learn. Otherwise, it will take time. It is not that easy, It is not that easy, because that's why the research is ongoing, you know. So even in the chat GPT, if you see, so they put around 70 billion plus, you know, just for the training purpose, and then for the GPU and everything. It's not that easy, you know, to get to the supercomputer, and then you need to have a large storage for the memory, and then you need to train your training algorithm also should be very efficient. You need to have a data set, everything, and then to build a more very giant AI thing, then you need to mix a lot of algorithms there, right? Okay, so let's study this basic one. Okay, so this is the basic one. So I have put for basic from every episodes, so we'll have some understanding lah, kan, right? We'll have some basic understanding how the agents are moving. Okay, so let me explain one by one. So if you try, this code is I really appreciate. Okay, so you also will experience. This is the first episode. So this is the 1111 as I showed earlier, right, in the grid world. So if it is not showed that if it is reached there, it will receive positive 10. But it will receive positive 10 when it reach the final point. Okay, so this is after the first episode. What will happen to the Q value? Okay, so again, as I said, this is not deep reinforcement learning. So this is reinforcement learning. If deep reinforcement learning, so all this state space will be under the network. So network will update. Here the Q function, it is updating, but in the deep Q network, the network is updating. We will have the target network. So the target network also will be updated. The normal network also will be updated, but the long function, it was from the target network, because we do have the target network. Okay, but let's examine this, the basic one, right? So I believe if we understand the basic, if we know much better, a lot of things we can do, a lot of things we can create, a lot of things we can develop. Okay, so let's see this. This is the Q value function for the up. Okay, this all means that at this location, this is where if the agent move up, it will get negative 0.2. Okay, at this location, at that same location, in this down matrix, and this is the down matrix, this is the matrix for up, this is the matrix for the down. If the down matrix means that if it goes down, it will get negative 0.28. So in the same location, if it move left, it will get negative 0.2. In the same location, if the agent move right, it will get negative 0.9. Negative 0.9. Okay, negative 0.19. Okay, so this is the after first episode. Okay, so this is where it updates. So this is how the agents move. You see, the agents move to the exit, to the goal point by like this. So it took like this lah. Means that it moves from here to here to here, and then maybe it hubs here, and then maybe it's somewhere here, maybe because of the exploration, and then finally it reaches here. So this is in the first episode. Okay, so after the first episode, this is the Q table. Now in the second episode. Okay, so in the second episode, okay, so we can see the agent taking path like this. This is not same like the second episode. If it's by the rule, if it's by the heuristic or something, you know, normally it will take somehow the same path. But here is the difference. It is not following. You can see here, right? It is not following the same one. No, it is by itself. That's somehow the beauty, the beauty of AI. So somehow you need to understand the beauty. Where is the beauty of AI, right? So you can see here in the episode 3. In the episode 3 is moving like this. It took some time because we do have the exploration. So that's how the research is moving. So we cannot claim the reinforcement learning, this basic reinforcement learning is enough. No. Of course, and then why they have this A3C, the soft active predictive, and then somehow why they are introducing the physics-informed neural network. And then some people researchers are trying to put already this physics-informed neural network inside with the deep reinforcement learning. Why the research is ongoing? Because we want to improve and improve. So mainly it is more on the explainable AI. Explainable AI. What we call, when we say explainable AI, what we understand by explainable AI? Right, when the network is converged, then the network is converged. For instance, here I also say the model is converged, right? So, but when we look into the converged model, what we will see? We will see the updated weights, the network, the final converged network with the updated weights and etc. So, anything we can learn from that? We cannot examine. We cannot get anything from there. Can we get anything? So any application you might have, previously we do have a lot of classification, recognition, a lot of experts are there, like Dr. Hassan, Dr. Jazlan, our Dr. Rimaz, Dr. Aiman. So all of them have introduced a lot of things in the the classification, recognition. Finally, in the network, in the updated, in the converged network, what do you learn when you see there? It works. I didn't say it's not. It's work, but with whatever that you want, right? Whatever that you want. But the network itself, what do you understand when you look into that? It's only numbers. That's why the researchers are moving to the physics-informed neural network. I'm just saying why they need the direction. It's already the good already there, but they're trying to improve. The researchers trying to improve. That's why the basic understanding we need to have. Basic understanding we need to have that. Why we need to have where the researchers are on moving. So same to here. When we look into this one is working. This one, but when you look into, but this is the result, right? I'm not saying about the result. I'm saying about the converged model itself. When you look into the model, we don't understand. And then that's why because we are moving to the ethical AI and everything, so we want to make the AI explainable, right? So that's one of the research are ongoing there. Even in the deep reinforcement learning also same, so that the decision making of the agents, decision making of the rewards, it is understandable. The final converged model, it is understandable. That's the basic lah. Okay, so this is in the episode 3. So when we move there, this is in the episode 4. It's getting better. It's getting better, right? The path is getting better. It's getting better. But when you can see the episode 5, again, you try new. It's already reached, as you can see here. So this is somehow better than previous. But since because of this exploration, we do have, I explained earlier, we have this exploration. So this, because of this exploration, now the robot is trying here. So that's, if you can see, this is how the AI agents are deciding by itself. The AI agents, you can try this code, and then you might change here and there so that you can learn by yourself what's happening there. And then this is the episode 6, still same. And then episode 7, it's getting better. It's not no more. If you compare episode 6 and 7, this is much better. 7 is much better. Right. And then now episode 8. 9 is already getting again clumsy again. It's moving. I believe this is because, even though your exploration, let's say 10%, but the randomness, the probability, it is from the computer. So you need to understand, this is not saying that our algorithm is not working. So that's one point. Because of the exploration. And another thing, that's why the researchers are making better and better the algorithm. Okay. So a lot of things we learn from this 10 episode. This is final one. This is the 10 episode. I just put only for the 10 episodes only. Oh no, until 20, I think, I guess. This is 11, and then 12. This is 13, 14, 15. All of them are not same until 15. Yes, until 15 I put. So this is the final one. So that's how it's evolved. So you can try first if you want to try, or if you have any questions you want to ask, I'll be free. So if you want to discuss anything, yeah, if I can, I'll try to explain.
You can unmute your mic and ask the question, or you can put the questions in the chat box.
Yeah, any questions? Explain link of Google Colab. So Dr. Rimaz, you have passed the Google Colab, the code, right? I think I have passed the code to the coordinator. You just copy and then you can run in your Google Colab. So am I okay? Srijana, you can ask the coordinator. I think I've passed in the morning already. I've passed the code. That's the same code. I didn't do anything, and I didn't revise anything there. Okay, Umera Banu asked about the exploration and exploitation. Okay, let's move again to the exploration and exploitation. Okay. Okay, so in the basic one, so we do have, I said, the plan and now the policy. So policy means we want to guide the robot or agent to move. So here we do have two. One is exploration, another one is exploitation. Exploration means it will try to discover the new actions. It can be random, it can be guided by something, okay, but the original one, it is random. Random means, okay, so let's say I put, okay, I have a dice. In dice, you have six faces right there. So 1, 2, 3, 4, 5, 6. Six faces, right? So let's say I put 20% of exploration. No. This is quite difficult because dice, we have six faces. Six faces is quite difficult to change to the percentage. Okay, it will be quite difficult. Let's make this is a very easy one. Okay, let's say I put 20% of exploration and 80% of exploitation. Okay, so let's say you have anything that you have a 10 pieces of sheet there in the kind of you need to take one, you have 10 only. So that it can be that you in 2 out of the 10 it will be the exploration. The remaining 8 it will be the exploitation. So by random, computer will select the policy. If at that time it is on the exploration, so means that the card that been taken out, it is the exploration, then the robot will try to find the new action. It is not guided by anything. The previous one, nothing is affecting the exploration. It will just try, and then when it reach there, then it will get some. It will reach in the new state, and then it will get some reward or punishment. So let's say here, for instance, here again, here the robot at this location. The robot is at this location. Okay, and then now the probability was taken, was drawn, and then the decision was for the exploration. If it is exploitation, of course it will move up. But at that time it is exploration. Exploration means it can take any actions. Okay, taking any actions also, it is randomness. Just random actions. Okay, let's say at that time it took at the right. It reached to the fire pit, and then it will get the punishment. And then the agent will know already, oh, I cannot come here. So it will update its knowledge. At this location, I cannot move to the right. But again, if it's exploration, and then the random also going up, bringing right, we cannot do anything. That's why at the beginning, the exploration will be higher, the normal, the exploration will be higher, and then towards the end, exploration will gradually become very, very minimal. Exploitation, it will be what? It will be the stored Q value or stored value function there. So the reward or functions or whatever, when I reach here, I will get this. It is already been stored there. So from that, it will take the best one. So let's say at this point, now the probability was going for the exploitation. Exploitation means it will take the maximum one. It already knows that if it is not known, then it will just take, so at the beginning, it will just update by itself. And then when it reaches there, and then it will update its knowledge. The matrix will be updated. So for when I say the knowledge, it can be the matrix. Okay, the matrix will be updated. For instance, here the easiest one for here. The matrix will be updated, and then it will take the best one, which is up. So maybe I will show here. Maybe in the code itself. Yeah, okay. So maybe now the robot is here, okay? And robot at this location, in this location. Okay, so now the turn is exploitation. Okay, so I think you can see my arrow, right? Okay, in this location, which one is the best? Going up is negative 0.19. Going up is negative 0.19. Going down is negative 0.1. Same location, I'm pinpointing the same location. You see here? So this is for up, this is for down, this is for left, which is negative 0.21. This is for right, negative 0.1. So which one is best? Negative 0.19, negative 0.1, negative 0.1, or negative 0.21? It is obvious either down or right, which is negative 0.1. So it can be randomly chosen between these two. Because this is the best one, right? This is punishment, right? This is bigger punishment. This is the biggest one, negative 0.21. So the smallest punishment, it is this one. So these two, it will take the best one. So this is exploitation. So for instance here, right? Okay, you can see here, this one, at the episode 7. So now I'm pinpointing at this location, at this location, you see, at this location. Okay, at this location, so I hope you can see my arrow. Okay, so at this location. So going up at this location, if it goes up, it will reach what? It will get minus negative 0.1. But at the same location, if it goes down, go down means we don't have the obstacle. It will same, right? So going down, it will reach it will get negative 0.1. Going left is negative 0.11. But going right, 2.7. So at that location, if it is exploitation, of course it will take the right. Then it will get to the goal point. You see? But at that location, let's say at that time the computer do the exploration, let's say 0.5 only, 0.05 only exploration. But it turns out at that point, exploration was chosen. Then it cannot be anything. The exploration means that it can goes to the left, can go to the up, can go to the right. So that's the difference of exploration and exploitation. So I hope it answers.
I think very well explained, sir. I would like to ask you that can you highlight more on your MATLAB example with the LiDAR and perception sensors like camera, etc. Can you detail about it further, sir, for the interest of the audience?
Yeah. So that will take some time. That will take some time,
It's okay, sir.
because that's, I need to go into the deep reinforcement learning first. But I can give you some highlights there lah. Okay, so in the deep reinforcement learning, same, somehow the reinforcement learning, it will be same, but as I said, it will be in the in the network. Okay, so let's focus on the LiDAR only. So there we have only 7 points. We have fixed only 7 points. Seven points only for the LiDAR. So to imitate the robot is to guide the robot so that the agents moves forward. So we didn't include the 360 degrees. So means that the robot is perceived the sensors we have limited to the front only, so that it will, whatever the guidance is only to these they have 7 location only. From field of view, yes, field of view negative from if I am not mistaken, from negative 135 to 45. Oh no, 30 degree. Yeah, from 30 to negative 150 to 150. So it is like that only. Okay, so as you can see my hand, so it is like that only. So that's the angle that's only be covered. That whatever the angle, that will be the state space. Okay, so that's the the location that the robot can move. That the robot can move 360 degrees, but that the sensors that robot, it is updated. Okay, so and then we do have also fuzzy logic to guide to better explain the reward functions in the deep reinforcement learning for that work. But you can also go with the basic reinforcement learning where we put some rewards, but it will take some time for the robot to learn. Okay, so we have used deep DDPG there, not DQN. So that's one is more continuous. If DQN, what's the difference between DQN and DDPG? In DQN, it is more discrete. So the movement will be up, left, or whatever that we have. It can be 7, it can be 5 also, but the movement is discrete. The movement is not continuous in the deep DQN. So from the QN, from the Q value, so when the network, when the deep learning it's inside, it will be share. No, I didn't share this MATLAB. So I'm just talking only because I didn't prepare for that MATLAB. So okay, so it will take some time if I wanted to move there. Okay, so I'm just explaining only. Okay, so in the DQN, the Q value, it is more discrete. That's why we can say up, right, left, down, right. And then deep QN also, it is discrete also. Okay, but it can solve for the robotic movement. Even for my turtle board there, it is DQN. It is not yet DDPG. But in our simulation work, we already have the DDPG where it is the continuous. So we need some time to translate it to the real world, but we are working into that. Right. Okay, so if you have any other questions, a lot of works are ongoing. Lots of works. So some of them, as I said earlier, some of the labs are focusing on the DRL with the optimization. So they're trying to optimize the DRL further better. And some of them are they are working on the physics informed. So even physics informed neural network are ongoing research. You might know, you are better than me. A lot of you are researchers are better than me. So physics informed neural networks are also ongoing. And then we do have also liquid neural network. So all these also can be coupled with the deep reinforcement learning to see what's happening. But of course, we need the application also should be much complex. If it is this kind of application, so why you might be asking why I need to couple with the optimization, to to physics informed neural network? No need, right? So of course it depends on the application. Some of the application it is very very easy. We just can solve by if else. Then why you need the network there? No need. So of course all of them is application based. Some of the applications, if else is better, you have a very clear, distinct decision, then proceed. Why you want to make yourself harder, your computer also complex, just makes it easy. It depends on the application. Some of the applications are very complex, so we do have, like in the chatbot, like in the a lot of agentic worlds. So we need to have a much better algorithm to promote the convergence, to promote the learning better, to make the agents understand. Right. So please let me know if you have any other further questions or anything you want to share.
Participants are requested to ask questions if they have.
Okay. So how moving obstacles behavior was configured. So as I said earlier, so we have coupled our DRL with fuzzy logic. So this is ongoing work. There's a okay. Yeah. So means that we do have the fuzzy logic in the DRL. Okay. So then by that we configured much better. So we have the, without fuzzy logic, what is happening, all the results we do have, but of course we do have the the algorithm there. But I can give you some highlight. So we have used in the as I said earlier, we do have the reward function, and we do have the policy for the exploration and exploitation, right? So we have put the fuzzy logic or any other optimization. We have ongoing works on optimization also. So we have put optimization also in the exploration and the reward functions, so that it will promote the robot to know, to agent to understand better. The knowledge representation will be better. So if you're ongoing, if you're finding the paper on the expert system and everything, so you have a lot of works are ongoing to, ongoing works on the knowledge representing to understand, to make the agents understand better. Sorry, I couldn't share more than that. So if it is because yeah, maybe next next any other session. But certainly I will share later on, but not now. I think it will take time before if I wanted to move there. Sorry, I was talking just now. I'm not sure whether it's not. I was saying that, of course, we do have the fuzzy logic and the deep reinforcement learning in the for the moving obstacles. So means that the fuzzy logic it was there. So to make the robot to agent understand better, to find that this is the moving obstacle, this is the this is the goal, and then in the exploration also. So that's how we promote the learning make much faster. Okay, so that's ongoing work. So of course, if I move there, it will take a lot of time. So I'll be very open. If you can email me, I will share with you.
Thank you, sir, for your wonderful explanation and demonstration for the.
All right, thank you, everyone. So thank you. Thank you for the good feedback also. So I really appreciate if you have anything, you can email me. My email is here. I'll put here. Dr. Rimaz also has my email. All right. All right. Thank you. So if there's
Thank
no,
you, sir, for your
yeah.
uh, wonderful explanation about reinforcement learning, where we learned about the agent, environment, action, rewards, policy in depth with the different examples. We got to learn more about this in depth. So we would like to take it into further also in our research. And I request all the participants to go through whatever the things has been given and the resources has which has been shared. Then only we can come up with some good outcome. So I request Dr. Azhar. I would like to thank Dr. Azhar to whatever he has given the lecture. We will further take up into the actions. Thank you, sir, for your explanation.
Thank you. So can I leave the room?
Yes, sir.
Can we take a picture together?
Yes, sir. We can take. So I request participants to have the video.
Sir, you can stop your presentation, sir.
Yeah. Okay. So please send to me the picture also later on. Right, done? Right, done? Once more. Okay.
Thank you, sir.
All right. Thank you. So all the best.
I would also like to thank all the dear participants, those who have enthusiastically, patiently has joined this session, and we are very thankful to all the participants for joining the session on time. So hopefully we'll have the everybody will be joining tomorrow as well. Okay, we have very interesting talks lined up even for tomorrow. Just 2 more days to go to complete our FDP. Thank you all for your support and cooperation.
Thank you.